In this video, I'm going to talk about solutions to the Schrodinger equation for a hydrogen atom. And so a hydrogen atom is an atom that has just a single proton in its nucleus. And so we want to model the potential energy for this nucleus. And so in the previous videos, we talked about an infinite spherical potential, and we can actually use the same spherical harmonics for that because at each level, so at each particular distance from the nucleus, we have the spherical harmonics. So it's going to be the same as on the infinite spherical potential, but now we need to look at the radial equation. The radial equation will be different because now we don't have a certain potential from this distance to this distance and then an infinite potential after that. Now we have a gradually decreasing potential as we go away from the nucleus, which is this proton. And so this right here, this potential, we have the potential here, and we also have this, which is that same centrifugal term that we saw in the infinite spherical potential, and that's essentially just the pseudo force that's sort of pushing the electron away from the nucleus as it's spinning rapidly around the nucleus. And so the potential we're going to use is the same potential that you might have seen in a freshman level physics class, which is the electric potential modeled with the Coulomb equation. And so that's the K times our first charge times the second charge over R. And remember, this is R, not R squared, because we're not talking about the force, we're talking about the potential here. And so this V right here, so this K, which I will show explicitly here. So we'll call the two charges E squared because it's the charge of the electron times the charge of the proton, which is the sort of same but opposite charge. And so we'll put a negative there. And then we have 4 pi, and then this epsilon naught, which is the permittivity of free space. And that's all what this K is here. And then we have R right there. And so what we're going to end up with for a potential if we want to model that here in one dimension. So we have the origin here. This is R, and the y-axis is the energy of the potential. And so when we're really close to zero, when we're close to our proton here, close to our nucleus, this R squared right here is going to start dominating this single R right here, because if we take a really small number times a really small number, we get something extremely small, and this is in the denominator, so it's actually going to make this whole term here extremely large, and in fact it's going to blow up towards infinity as we get closer to zero. And so our potential is asymptotically going towards infinity, and what I'll talk about here, so we will get a potential that looks like this, and then it asymptotically goes towards zero as our R becomes very large. Because as our R becomes very large, then this term right here, this centrifugal term, will tend towards zero extremely fast, and so that is our positive part. So this potential here is the negative part, which is why we're in the negative right here. But this is also going to tend towards zero, though a bit slower than our positive part. And so we're going to tend towards zero as R becomes large, because this R in the denominator is going to become larger and larger, making this potential here go towards zero, and it's negative, and so it's going towards zero from the negative. And when we're down right here, that's when our potential, our negative potential here is sort of beating out the r squared here, um, and so we end up with this negative potential, and that is what we would want, because a negative potential, the lower the potential, the more tightly it's bound to that proton, to that nucleus, and so the electron is going to fall into this distance from the nucleus that is the most negative right here. And so that is going to be the distance we are from the nucleus here. And so the rest of this video is going to be fairly math heavy. I mean, all of quantum mechanics is math heavy, but I'm talking about there's going to be substitutions, there's going to be algebraic manipulations, and so it becomes kind of easy to lose sight of what we're actually doing. Um, I think it's useful and illustrative to go through this math, but if you kind of want to uh, sort of jump to the conclusion, you can probably skip to my next video, which is where I'll pick up with actually solving the differential equation. The rest of this video is essentially going to be getting us to the type of differential equation that we want to solve. And as we'll see in the next video, we'll be using the associated Laguerre polynomials to solve the differential equation. So, like I said, the rest of this video is essentially just getting us to the differential equation that we want in order to solve that differential equation. But I think it's useful to go through this. Some of these steps that I'm going to go through here are sort of skipped over in the Griffiths textbook, which is what I've been going through once we've gotten to this three-dimensional stuff, which is where that student's guide that I was using sort of stops. That one only goes through the one-dimensional stuff. So if you're using the Griffiths textbook and you're confused about some of the steps in it, I think it would be very useful to watch this video, because I'm going to explicitly go through some of the steps that Griffiths skips over. But anyway, now that we've substituted this into our potential here, we're going to want to get our equation into a form, into a different form. And so this here is the equation with this potential here substituted in. And so this is all stuff, so I just wrote it down here rather than going through the video writing it to sort of speed things up. But this is all stuff that gets kind of skipped over in the Griffiths textbook, where the Griffiths textbook goes right from this equation and skips over all this and then gives us this equation here in red. So I'm going to go through this here fairly quickly. So the first thing that happens is we distribute or factor out this h bar squared over 2me, and we see that the potential term here doesn't have that, so we actually have to put an h bar, or a 2me over h bar squared into that right here in order for it to be the way that this, if we distribute it back in, would just end up being equal to 1. So we're going to factor that out, and at the same time we're dividing both sides by this e here. And so that's how we end up with this h bar squared over 2m with this subscript e here, meaning that we're explicitly using the mass of the electron, and then our big E here, which is the energy. And so this allows us to make this substitution right here where we're using K. The Griffiths textbook uses kappa, but I just find K easier to write. So I'm using k. So we're setting k, and maybe even use the three line here to show that we're sort of defining k as this. And so then we can set this all equal to our kappa here, and then we can distribute it back in. And what we end up with is, because what we had to do here in order to factor out was essentially have this have the h, or the 2 times m sub e over h bar, which is essentially 1 over k, and so then we end up with this k down here. And so when we distribute the k back in, we end up with a k here in the denominator, and then we have this other k here, and it's sort of suggestively separated out that way so that we have this kr right here, because we're going to use that to make another substitution. And so we have this right here, as I said, so this minus 2 me times e over h bar, and we're going to distribute that back in right here. And so we can see that this is sort of the upside down version of what we have right here. And so that's how we end up with the k's in the denominator. And so we will end up putting that k sort of right here, and it's squared because what we have here is not the radical version that we are using right here. And so we end up with the kr and then all of that squared here, and we're still times this u and then equal to this u here, which we got rid of the e from that right here by dividing the whole thing by e, if you remember. All right, and so now from here we're going to subtract this in square brackets from both sides. And so then I wrote it explicitly like this. I sort of distributed this u back into here. So now we have u minus this potential term here times u plus the centrifugal term times u. Then I just factored out the u, and we end up with this whole thing right here. So this is the equation that Griffiths ends up with, going directly from this first one right here. So once again, to recap, I divided both sides by e and factored out this h bar squared over 2m sub e, which gave us this. And then I made this substitution, this k defined as this square root of minus 2m sub e times e over h bar, and then when I distributed that back in, we ended up with this right here, where we have our e squared times m sub e over the 2 pi epsilon naught, which is our permittivity of free space, k. And then I sort of separated one of the k's out from here with the r, which is our distance from the nucleus, so that when I make another substitution here in a little bit, we won't see. And so this right here should actually, I forgot to put that 1 over r in right here, so that 1 over k r should be in right there as well. And so now we can pick up where the Griffiths was going. And so Griffiths starts by making 2 substitutions. So rho, which my rho's are just going to look like p's, and I might accidentally use p and rho interchangeably, but this is supposed to be the Greek letter rho, which is kind of a weird thing that maybe sort of has a bit of a curve like that, but I'm just going to because I'm going to be trying, I don't want to sit there trying to write it slowly every time. They're going to look like P's. I'm going to call them rows. I might accidentally call it P sometime, but we have rho equal our KR. Then we will have a rho sub naught be our our M sub E times our charge squared. That will be over 2 pi epsilon naught. And then we have our h bar squared k. And so this should actually have an h bar in it too. So there should be an h bar in there. So I'll see about writing this a little bit neater. So I'll remove all this stuff here. And so it should be this epsilon naught h bar squared and then k, and then there's the k, 1 over kr right there. And so we're sort of defining this whole thing right here as our rho naught. And then we're defining this kr and then this kr here as our rho. And so then what we end up with after making those substitutions is we have our d square u, and now it's d rho squared because we are making that substitution. And so then that will be equal to 1 minus rho naught over rho plus L times L plus 1 over rho squared, and then U. And so that's what we end up with after making these two substitutions here. And then so what we want to do is we want to look for solutions to this, and here I'll sort of circle this in blue so we remember that this is an important one that we're thinking about. So we want to solve this for, we want to solve it for when rho goes to infinity and for when rho goes to 0. And so it's easy, it's nice to think about rho. So rho is essentially what we're replacing r with. So we want to look at where rho is going to 0. So that would be this asymptote right here. And we want to look at where rho is going to infinity, which would be this asymptote over here. And so we want to look at where this asymptotes. And so the first thing we're going to look at is when rho goes to infinity, what we end up with is this rho and this rho squared are going to become very large. So everything except this 1 here is going to essentially go to 0. And so when rho goes to infinity, we have our second derivative of u with respect to rho is going to be equal to just u, because it's just u times this 1 here. And so with that a general solution, and if you're more interested in how we get these general solutions, I highly recommend my differential equations playlist. So this u, which is a function of rho, is the general solution is going to be some constant times e to the minus rho plus some constant b times e to the rho. But we see that if rho is going to infinity, this part here is going to blow up to infinity. So we need to set b equal to 0. And then so our solution is going to be some constant times e to the minus rho. And then so we also want to look at solutions as rho goes towards 0. And so as rho goes towards 0, once again, we're going to see that this, because this very small number times a very small number is going to become uh, a much smaller number. So this rho squared is going to start dominating. It's going to dominate even this row here, even though that is going to be a small number. A small number times a small number is a much smaller number than even this small number here. In fact, it's exponentially smaller. And when we have a small number in the denominator, then it makes this a much larger number. And so we have our d squared u over d rho is going to be equal to our L times L plus 1 over rho squared u. And then so a general solution to this is, so our u, which is our wave function, as a function of rho, is going to be equal to some constant times rho to the L plus 1 plus some constant times rho to the minus L. But once again, we see that this is going to blow up to infinity as rho goes towards 0, because what we can essentially think of that is of rho to the minus L is 1 over rho to the L. And so as rho go towards 0, this is going to blow up towards infinity, so we want to set d equal to 0, and so we're going to have this be equal to some constant times rho to the L plus 1. And so what we're saying is that this e to the minus rho and this rho to the L plus 1 is our asymptotic behavior. And so we have our e to the minus rho times our rho to the L plus 1 is our asymptotic behavior. And so we have our u, which is a function of rho, equal to that. But then there is also that part here where we are not in the asymptotic behavior, and so we need a function for that. And so we are going to call that function v, which is a function of rho. And so we end up with this here, which I will now circle in green, because this is kind of another important one that we might want to look back at here in a little bit. And so we have this here, and so we are looking for, though, this second derivative right here. And so we want to take the second derivative of this. So the first derivative, du over d rho, is going to be equal to, and I'm not going to go through all the product rule here, so just know that I'm using the product rule for this. So we have our rho to the L power times e to the minus rho, and that will be times L plus 1 minus rho v plus rho times dv over d rho. Then if we want to take the second derivative, we have the second derivative of u with respect to rho. So it's just taking the derivative of this now. And what we end up with is kind of this long string here. So rho to the L, e to the minus rho, and then that is times minus 2L minus 2 plus rho plus L times L plus 1 over rho, close the square bracket, v plus 2L plus 1 minus rho dv over d rho plus rho d square v over d rho. and then we'll close that bracket. And so then what we want to do is, because we have this right here, this du, this d squared u over d rho squared, we want to set that equal to this because we have d squared u over d rho squared. And so from that, what we're going to end up with, if we set this all equal to each other, so I'm going to ignore this part here for the time being, because really what we're going to be doing is some algebraic manipulation on this part here, and it's not going to affect all this. So just for the sake of not having to write all of that down, I'm going to ignore that part for a moment here. And so we're going to take that equation from above. So that's the 1 minus rho naught over rho plus the L times L plus 1 over rho squared. And we're going to set that equal to this up here. And so this actually, since if we look back up here at this blue, we have all this times this u here. Now we want times v, and so we're actually going to make this substitution into there. And so what we end up with is times v, and we then have our e to the minus rho times rho to the L plus 1. So our e to the minus rho times our rho to the L plus 1 is equal to our rho to the L times e to the minus rho, and then that multiplied by our minus 2, and I'm going to factor that minus 2 out, so we end up with L plus 1 plus rho plus L times L plus 1 over rho. And so we have that, then v, and then we'd have the plus that other stuff here, but since what I'm going to do isn't going to affect any of that, I'm not going to write it in. And so what we want to do then is we want to divide both sides by rho to the L e to the minus rho. Divide this side by, well, I'll just write it in the reverse order since I have that written that way here, and then rho to the L. And so this is going to cancel, this is going to cancel, this is going to cancel. This L is going to cancel from here, so we end up with just a rho. And so if I distribute that rho into here, then what we end up with is rho minus rho naught plus L times L plus 1 over rho, and then that is equal to the minus 2 L plus 1 plus rho plus the L times L plus 1 over rho. And these are all times v, so we can distribute the v in here, we can distribute this v in here. I'm not going to write it just right now, just for the sake of keeping everything a little bit tidier looking, because right now we just want to do some algebraic manipulation here. And so essentially what we're going to do is we're going to subtract rho from both sides. We're going to subtract this from both sides, and so what we end up with is minus rho naught is equal to minus 2 L plus 1, and so we end up with that. And so then and so this once again is something that that is skipped over. Zoom back out here, is skipped over in the Griffiths textbook. It sort of goes right from this point here and then kind of goes right, well, it even goes past this point here, and then just gives us, it just gives us the rho d square v over d rho square plus 2l plus 1 minus rho dv over d rho. And that's all the stuff that I was leaving off. So all this stuff right here. But then now all the stuff that that I was just working on. So that's plus, we'll do a square bracket here, rho naught minus 2 L plus 1, and then that is V equals 0. So Griffiths kind of skips over a bunch of those steps and then just brings us right to this. And this is the part, where when I first read this book that really confused me. So like I said, he goes from the second derivative actually. So, and I will circle that in yellow just to kind of remember this second derivative here. He kind of goes right from this and then sort of skips over all this stuff and brings us right to this. And that part confused me because I wasn't sure exactly what was going on. So I thought it important to sort of go through those steps explicitly. And that's where I'm actually going to end this video, because this equation right here, this is the differential equation that we now want to solve. And that's what I'm going to be talking about in the next video, is actually solving this differential equation here. And so, like I said, that's what I'll be talking about in the next video. And what we'll see is we ultimately end up with the associated Laguerre functions for solutions to this. And once again, remember, this is the radial equation. We're trying to find solutions to the radial equation because we can still use the same spherical harmonics that we found for the infinite spherical potential well. And so anyway, I don't want to ramble on. I hope you found this video useful, especially if you've ever looked through the Griffiths textbook and were confused by some of these steps. But anyway, I hope you found this useful, and I will see you in the next video.